Hey everyone, this is Team Willard and we're gonna talk about shape modification tools. The topics we're gonna cover under the shape modification tools are control point repositioning and weight modification, warping, flattening and bending, and uh, with design examples and geometric modeling lab. Coming to part 1, the technical details. So a NURBS curve or a surface is defined by its control points, weights, and knots. Modifying any of these changes the shape of the curve or surface. So in this chapter, we develop tools which take such constraints and shape specifications and convert them into modifications in control point locations or weight values, which are generally preferred by most of the designers lately. And the influence of the control points and weights on shape is geometrically clear and intuitive. And whereas coming to the topic, this is about specific point, multiple point, and derivative constraints, and converting the geometrically intuitive inputs into control point relocations and into weight modifications. So the methods of this chapter are very local due to the local support property of the B-splines, and however, the extent of the curve or surface region which is to change can be made smaller by knot refinement or larger by knot removal. Coming to control point repositioning. So B-spline curves or surfaces can be superimposed to form a new surface or a curve. In other words, if a collection of surfaces are all defined on the same UV knot vectors, then the surface is well defined by the same knot vectors and control points, where is defined by the given formula, where alpha k are the scalars and pij are the control points defined defining the surface. This suggests the use of additive or corrective surfaces or surface patches. One can work with small, simple pieces and then superimpose them to form a new surface or to modify a region of an existing surface. Boundary conditions are easily controlled. This method was used by several authors to present the interactive surface design. Down below you see the formula where it denotes the new translator control point for pk and the translation vector by which is represented by v. The previous equation expresses a functional translation of all curve points Cu which lies in U, and all curve points outside this interval are unaffected. The maximum translation occurs at the maximum of the function, and this is illustrated in the given figure. And as you can see, the formula where which is alpha equal to d by v mod rkp into U. So the figure which is shows the moving of point C by repositioning P4. There are two approachable methods to control point repositioning from the user point of view, whether he picks the control polygon or the curve. In the first scenario, the user might specify a vector direction and distance and then pick a point on the control polygon. If the picked point is an existing control point, the system simply translates it and redraws the curve. If not, then the system makes the point a control point through inverse knot insertion, and it subsequently translates the knot control point and redraws the curve. In the second scenario, the designer picks a curve point P and then picks the point P to which P is to be moved, and it remains for the system to choose and control point Pk to be translated in order to produce a desired movement of P. The parameter value, which generally lies quite close to as a maximum of an arbitrary basis function, is so-called node and is defined by the given formula. So note that the averages of the knots which are interior to the domain range is non-zero. For the interactive control point repositioning, we recommend choosing k based on the node values instead of actually computing the maximums of the RIPUJ, that is k, which is chosen by the given formula. And these two figures illustrate the examples where the points are repositioned and the corresponding nodes are given and the curve degrees are different from each other. So now in control point repositioning, let's talk about moving one point. So where the previous figures 11.2 and 11.3 show two control point repositionings in which the index was chosen based on the proximity of U to the nodes. So in the first figure, it is pleasing, while in the second figure, it is asymmetric and not pleasing. So the reason is that the U is very close to the node, therefore the curve translation is rather symmetrical about Cu. But in the figure 11.3, the U lies halfway between the nodes, Therefore, the maximum transition occurs is towards the curve. So there are two solutions to this dilemma: inserting a knot in order to put node at U, or repositioning both pk and pk plus 1. So let's try inserting a knot U in between the forces to have value of U. So the below equation shows clear that where U lies between the given limitations, hence the formula shows the necessary equation. So coming to the examples, suppose we now want to move P along the distance D by translating both the pk and pk plus 1 in direction. So it gives the pk plus 1 equal to pk plus 1 into gamma alpha v. So the parameter 1 allows us to vary on a linear scale the movement of pk plus 1 related to one another, and designer can set any of his value, any value, or a good default is given by 11.8, and the alpha is given by the given like the below formula 11.9, and the both figures shows a symmetrical curve repositioning. Now coming to moving 2 points at a time. In the figure 11.6, if we observe, both P3 and P4 are moved, and clearly the disadvantage with this method is a broader domain of change, and the B part of the figure shows the moving of P3 and P4. So using these tools, it is easy to implement a user-friendly interactive graphic interface for control point repositioning. And by noticing that, furthermore, only that portion of the curve which is in the image is graphically updated for each repositioning. Coming to the examples of moving 2 points. This figure 11.7 shows incremental repositioning of one control point. So finally, a designer can easily restrict the domain on which the curve should change by picking 2 or more curve points, and which determines parameters, or if are already not knots, then they are inserted one time each. So knots should be inserted with multiplicities greater than 1, because this can cause unwanted discontinuities when control points are moved. The figure shows a pull in the curve with equal increments by repositioning P4 x. These techniques extend easily to surfaces. For completeness, we state the relevant formulas given by SUV. So when let the SUV be a nurse surface, then we assume P equal to SUV, and it's translated along vector V, and distance D is repositioned by the control point pk. Then the pkl alpha is given by the given below formulas, which is explained clearly. Until now, we spoke about curves. Now coming to repositioning for surfaces. Analogous to the curve case, knot insertion can be used to restrict the rectangular domain on which the surface is to change, and inverse knot insertion can be used to obtain additional control points at specific locations on the edges of the surface control met. So in the U direction, if it is inserted by the formula, it's given by U bar, and alpha is given by this, where QV is inserted by V bar, and beta is given by the given below formula. So these two are the examples which show translation of one control point, and these two examples illustrate simultaneous movement for 4 neighboring control points. Now let's talk about weight modification. Control point repositioning has a translation effect on a curve. Weight modification has a perspective effect, where all curve points in affected domain are pulled or pushed along straight lines which meet at a control point corresponding to the weight being modified, where the curve definition is given by Cu. The weight Wk can be considered a variable, hence we can differentiate Cu with respect to Wk using the identity Rkpu, and by the quotient rule of differentiation we can obtain dou by dou Wk, and which results in the given below formula. Now let's talk about the modifying one weight in weight modification. Hence, the first derivative of Cu with respect to Wk is a vector pointing in any direction from Cu to Pk. We now prove by induction that the derivatives of all orders has this form. So, and assume the nth derivative has the form of a n pk minus Cu. Then by simplifying it, we get alpha n plus 1 is equal to dou by dou Wk with respect to alpha plus n minus alpha power n alpha power 1. So this completes the whole proof. It is easy to derive the recursive formula to compute alpha n plus 1 and thereby obtain the formula for the higher derivatives as shown below, where we result in alpha of n plus 1 equal to dou by dou Wk alpha power n minus alpha power 1 into alpha power n. So both the equations prove that an arbitrary curve point Cu moves along a straight line towards Pk as Wk increases in value. So now let's talk about more geometric approach. Coming to the example, this specific example, the points are defined in the as RMP, where you notice RM and other points on specific curves, but P can lie anywhere on the line between R and PK, and now M and P can be expressed as shown, where we can reduce S and T. So this equation is used to derive R, and thus we can have P equal to 1 minus RKP into R, RKP mu into PK minus is equal to 1 minus TR into TPK. And M is given by the given formula, where we can reduce S is equal to NKP into U by sigma NI P into UWI plus NKP into mu bar. This equation gives a clear picture of the points and their place. So by reducing all that from the above equations, we get WK equal to as shown. So the above equation says that WK is the cross ratio for the 4 points PK, R, M, and P. The cross ratio is a fundamental quantity of the projective geometry. And these two examples show the pulling of the curve at a specific point with equal increments, and by changing the weights from a specific weight to another weight, and the new weight and by generating new weight components. Now suppose if point P equals C is to be pulled or pushed towards or away from PK to a new location P by modifying weight, then D will be given. So the new weight WK is derived as given in the formula below. Okay. Now let's talk about modifying two weights at a time. So we consider now the simultaneous modification of two neighboring curve weights WK and WKH. Such a modification pulls or pushes the curve towards or away from the leg of the control polygon, where R and P are defined as follows, where AK and AK plus 1 are given as shown, and so if WK bar plus WK plus 1 are expressed in this form, then after some manipulation we get beta K and beta K plus 1, where the above equation says P lies on the plane of a barycentric coordinate system. This figure shown explains a simultaneous pull towards P4 and P5 by changing W4 and W5 at the same time. And the equations 11.2 to 11.31 result in a simple geometric method to solve for the unknowns and thus obtain WK and WK plus from WK. Since alpha AK plus 1, AK and AK plus 1 are barycentric coordinates with respect to R, then AK and AK plus 1 are given by the respective formulas. Another scenario is to allow the designer to pick the curve point P, and the system subsequently chooses the polygon leg to find two nodes such that the U lies between TK and TK plus 1. In this case, a knot can be inserted which puts U halfway between the two nodes, where you can see in 11.15 figure where the U is in halfway between few nodes, and the 11.16 gives a simultaneous pull at U equal to 0.612 at a distance is a direction different from RQ by changing the weights equally at a time. The new weights are also computed. So the modification of a single surface weight is similar to the curve case. So now assuming RMP are defined as shown, then MP can be expressed as M is equal to 1 minus S into R plus S PKL, P equal to 1 minus T into R plus T PKL, where S and T are given as shown in the formulas. So as shown in the example, where the surface push at U equal to V is as same and it pushes towards P4 at a distance D1, notice there's a perspective change in the surface shape. So all the above equations we can obtain a cross ratio where we get WKL. So all the given equations imply that WKL increases, T increases, thus the surface is pulled or pushed towards or away from the PK or point P. P moves along a straight line segment passing through PKL, thus a modification of WK changes the surface in a predictive manner. As P approaches PKL, T approaches 1 and WKL tends to be infinity. Finally, if P is moved to a new location, then the required new weight value WK is expressed as given in the equation below.
All right, so now we'll talk a bit about warping. Warping is used to arbitrarily deform a local segment of a curve or region on a surface. Warping can be divided into two different categories, either curve warping or surface warping. And then surface warping can be divided further into two other categories, but we'll talk about that later when we talk about surface warping. But for now, we're going to focus on the curve warping. And curve warping can be implemented by means of control point repositioning using this following formula, where F controls the shape, D is an upper bound on control point movement, and W gives the direction of the warp. Also, in this formula, P sub I represents a control point, P hat sub I represents a warped control point. The curve of the warp is going to be restricted to a segment that we choose between two different curve points, C of U sub S and C of U sub E. And if I skip ahead a bit here through the presentation, we can see here in the top right figure the two curve points selected, and the warp here is going to take place in between those two curve points. So the following function is a useful warping function that we can plug in for f in our above formula, where r sub max is equal to r sub 3 1/2, and r sub 3 t is the rational cubic b-spline basis function given by this function here, defined by this knot vector and these weights, where all those weights are constant 1, except for W sub 3, which can be set by the designer. Speaking of W sub 3, this figure shows how f of t can change for different values of W sub 3. So as we change the weights, and from this, we can see that a function like this can be useful to either push or pull a bump on a curve. So, now we're going to talk about the steps of curve warping. So first, we suppose that W sub 3 is fixed. Then, a warp distance d can be specified along with a warp direction w. W can come in a few different forms, either a variable direction given by this formula, or a constant direction given by that formula. Alright, and so on the figure on the right there, we can see our d and w both selected there. Next, the interval that we've chosen is refined, which gives control points P sub I, where I goes from S to E minus P minus 1. So it gives us control points in between our two curve points there. And so you can see right here, it's refined, yielding those control points. All right. Now, once the interval has been refined, the points can be repositioned according to the equation from earlier. To do this repositioning, we must assign a parameter t to each P sub I. If we let delta represent the total accumulated chordal distance along the control polygon from P sub S minus 1 to P sub E minus P, then we can denote by T sub I the accumulated chordal distance from P sub S minus 1 to P sub E minus P, normalized by delta. Then, P sub I is repositioned by this formula, which is the formula from before, but now we've substituted in T sub I into the equations f of t and w, where then I goes from S to E minus P minus 1. Once the points have been repositioned, knot removal is then applied to the interval on the curve. So here we can see the points being initially warped and repositioned, and then down here we can see we apply knot removal across the interval from here to here, and that gives us our final warp. Now, warps of nearly any shape are possible, and we can accomplish this by defining parameters, modifying the defining parameters, which is shown by the figures on the right, and we can also do it by modifying the functions w or f of t and w of t, which is shown by the figures on the left. So if we start with the figures on the right, we can see the effects of changing weights. These are the same weights that we were looking at a couple slides ago, and seeing the effects of how f of t would change. And so we can see how those effects then would change the warp here. And then down here, we're looking at the warp direction and how when we have different values or different functions for W, it can end up changing the warp shape. And then on the left here, we can see how different functions for f of t can very radically change the shape of the warp. So now we'll talk about surface warping, which is similar to curve warping. There are two different types of surface warping: region warping and surface curve warping. Region warping involves applying a warping function to a region of non-zero surface area. So in these two pictures, on the left one, we can see the region that we're going to warp, along with the control points within the region that are going to be warped. And then on the right of that, we can see the effects of the warp on the surface. And then surface curve warping involves allowing a univariate warping function to slide along a curve lying on the surface. So down here we can see the word NURBS drawn out using a polyline. Then we see the control points that fall within the gravity field along that line. And we'll talk about gravity field later when we get to surface curve warping later on. And then we can see the effects of that warp then on the surface on the right. So, first, we'll start with region warping. And when performing region warping, we start by letting R be a closed region in the parameter space of a surface S of UV. Within this area, we perform region warping by repositioning control points based on the following formula right there, which is similar to the formula from before. However, instead of P being one-dimensional and containing the points along a curve, it is now two-dimensional and contains the control points in the region. Just like in curve warping, knot refinement is applied, but now it's to the area U sub alpha, U sub beta, by V sub gamma, V sub delta, before using the above equation. Knot removal is also applied after repositioning control points in the region. A parameter pair S sub I T sub j must be associated with each control point P sub I j, where I goes from alpha to beta minus P minus 1, and j goes from gamma to delta minus Q minus 1. This is similar to the parameter T sub I that was associated with each P sub I from the curve warping formula and stuff. But now, since P sub I j is two-dimensional, we need a parameter pair to go along with that. These parameters are used to determine which points are to be repositioned, and are also used to evaluate the functions f and w of the equation above. Points are only repositioned by the above equation if u sub I v sub j is in the warp region R, where the following condition holds true, and there's the condition. I'll give us a sec to take a look at that before we move on to the next slide. All right. Let's move on. So here we've got the equation there at the top again. And f in this equation can be any scalar value function defined on 0, 1 by 0, 1. Just like with curves, B-spline basis functions are suitable for both pushes and pulls in the region. For rectangular regions, the normalized bivariate bicubic rational B-spline basis function can be suitable. And that would be given by this function, defined on the knot vectors S and T, and all the weights are set to 1, except for W sub 33, which is freely chosen by the designer. Other B-spline basis functions may be more suitable for other applications, such as a rotated univariate B-spline basis function, which might be suitable for circular symmetry. Defining a warping function over an arbitrary domain can be difficult. Just like in the pictures from the previous slide, the region warps on the pictures on the right were created using the following function here, which is f of st is equal to 1 if the point falls within the region R, or 0 if otherwise. This displays the control point that falls within the region at distance d in the direction of w. The vector w can be the surface normal at each point, or any user-defined vector. Now we'll move on to surface curve warping. First, when describing surface curve warping, we suppose that a curve c delta is a curve that lies within the parameter space of S of uv, and r is a distance measured to both sides of c delta along the line normal to c delta at each delta. Surface curve warping is applied then by repositioning all of the surface control points whose parameters u of s sub I and v of t sub j lie within the distance r of c delta. This distance is also called the field of gravity or just gravity field. These points, p sub I j, are repositioned according to the following formula, given by that, which is very similar to the formulas that we've been looking at a few times now. However, here, d sub ij is the distance of u of s sub I, v of t sub j, to c delta, and delta I sub j corresponds to projections of u of s sub I, v of t sub j onto c delta. And a good definition of the warp direction could be this formula here, where n of uv is a surface normal vector as we move along the curve. Just like in region warping, defining f can be difficult. In the pictures to the right, the following simple definition of f was used, where f of d sub ij is equal to 1 if d sub ij is within the field of gravity of the curve, or 0 if it is not. The most important step, though, in applying the formula that decides how points are repositioned is the computation of the d sub ij portion. This can be simplified if the curve that the formula is warping along is a polyline, such as in the pictures on the right, which show a polyline warp, where there are a series of straight segments, and the points around the straight segments that lie within the gravity field of the segments are chosen to be warped and repositioned. So on the right here, we have the word NURBS drawn out in a polyline. Then below that, we have the control points that fall within the field of gravity of that polyline selected, and then below that we have the effect of the warp. And that wraps it up for warping, so I'll pass it off to my next group member.
Hi everyone, I am Sadman. I will continue from the topic flattening. Flatten operator allows a designer to easily introduce straight line segments into curves and planar regions into surfaces. In flattening, no multiple knots are inserted, so the transition from the curved portion into the flat portion possesses the smoothness inherent in the original geometry. We see three figures in the right side of this screen. Figure A showing the original curve need to be flattened, and figure B and C indicating the flattened curve. Figure B and C are different because they are flattened based on two different systems. We will talk about this later in the next slide. Curve flattening consists three steps. First one is refine the curve knots to obtain more control points, then project some specified control points Pi onto the line, and then replace Pi by its projection. At last, we have to remove unnecessary knots. Here, first and last point are pretty straightforward, but the second point needs some more explanation. So here we discuss about this. We assume that curve CU and line L are given, and then we have to define a vector W that defines the line of projection, which can be defaulted to be perpendicular to L. If we look at the picture, we have the graph CU and a straight line L that is intersecting the curve. And then we also see W that is perpendicular to L. So the relationship between the projection pi hat and w is in the given equation, that is p hat is equal pi plus aw, where a can be positive or negative. Pi is projected only if it is local to the interval us ue. Pi is replaced by p hat only if p hat lies between 2 points q1 and q2 on the line. These last 2 points, these are basically telling us when we take the projection of a control point and when we replace that point by its projection. When we draw the projection, there are two approaches. In figure B, the approach is that we will take all the projection from one side of L. In figure C, we take only those projections that are local to CUS, CUE. Now here is a different case. In the previous figure, we saw that the curve and L was intersecting, but what if they does not intersect? So in this figure, we see that we have a line L and the curve C, but they do not intersect. And now if we follow the same system that we discussed in previous slide, so at first we have a region CUS, CUE, and then we take the control points in that region and we draw the projection. By following the procedure discussed in the previous slide, so we will get a curve where only a particular portion is flattened, leaving the rest unchanged. Next up, we have surface flattening. A surface region is flattened by projecting control points Pij onto a plane pi. The equation is similar to curve flattening, but in case of surface, we have I and j to define a point. That's why instead of pi, we have Pij in this case. Rest of the things are similar in the equation. And we also have a vector here like curve flattening. So vector w can be defaulted to be perpendicular to pi, a region RUV in the space of SUV defined by a boundary curve CUVW is equal UW comma VW. Pij is projected only if its influence is local to RUV. A projected R pi on the plane pi defined by a boundary curve C pi W, Pij is replaced by its projection only that lies in region R pi. If the plane intersects the surface pi, then instead of requiring a region RUV, a designer may want to specify that only those Pij lying on one side of pi be projected. Cobb in 94 suggests the use of additional planes to restrict the region of control net to be projected. So here we have two figures to illustrate the idea of flattening. We see in the first figure we see a plane and a surface, and in the figure at the bottom we see the flattened surface based on the base plane that was given. Thank you, that's all from my part. My partner will continue from the next topic.
Today we'll be talking about different modification tools, and one of them would be bending. Several authors have investigated circular bending of curves and cylindrical bending of surfaces. These authors develop equations based on trigonometry which points onto circles. Under these mappings, a straight line segment maps onto a circle and a general curve segment is bent in a circular fashion. Bending takes place in three steps. Define the region to be bent, bend the region by repositioning control points, remove unnecessary knots. We need to have a base curve with which we will be bending the original curve. We bend the region between CUS and C of UE about the curve B of W by mapping relevant control points Pi of CU towards B of W. An additional point O called bend center is required. Point Ri is obtained by intersecting each line segment OPI with B of W. Here are some of the equations that help us in bending. There are different cases when lambda equal to 1, pi equal to ri, when lambda equals 0, p cap I equal to O, when as pi approaches to p cap I approaches to pi as lambda approaches to infinity. Here we can see for different values of lambda, the bending region gradually assumes to be shape of the curve when lambda approaches to 1. The effect of positioning the center O within the circle can be seen on the right side figure. And on the bottom right figure, we can see the use of a parabolic bend curve to eliminate two unwanted inflection points in a curve. Till now we have talked about curve bending, now let's talk about surface bending. The natural extension of the curve bending sorry, surface yields a very general and powerful surface modification capability. The surface S of U is bent about a bent surface B of ST, either towards a central point O or a central curve O of W. If a point O is used, then point Rij is obtained as intersections of the line segment OPij, the surface BST. If a curve OW is given, then parameter Wij must be computed and Rij is obtained by intersecting OWij, Pij with BST. Projection is computed using the following formula. Sij equal to Orij by Opij, Tij equal to lambda Sij by 1 plus lambda minus 1 times Sij, and finally we can compute P cap ij. Now surface bending with a non-touching cylinder can be seen on the right side figure. The positive lambda bends the surface towards the cylinder, whereas negative lambda bends it away from the cylinder. And surface bending with a touching cylinder can be seen on the right side figure. Now let's take a look at the design examples of all the shape modification tools that we have seen so far. Here we can see that the curve has a different number of control points, and we can see the incoming and outgoing curvature for each control point. And here we can see the image has a different control points, and dragging those control points would distort the image. Here we also can see that the puppet wrap has different control points, and each control points give you the capability to distort image in specific areas. Here we can see the weight reduction of animated meshes. In the figure down below, we could see that the model was reduced from 45 weights down to 12 weights. Here's another example of flattening. Figure A shows you a 3D construction of a cylinder, whereas B shows the flattened texture image of the cylinder. Here we can see we have a control point, and dragging this control point would give you a distorted image of specific type. Here's another example of bending. We have three meshes, and these three meshes have been bent into different curvatures that can be seen in all the other three figures. Now let's talk about GM Lab for shape modification tools. We have taken a curve, and with different control points, we can see how we can change the curvature of the curve on the left hand side. This is a more detailed image of the above figure. Here's another example of bending. We took a cube and we have reduced its size and extended for it to look like a long square object so that it would be convenient to bend. But if we see, we only have like 4 vertices over here. For that, we have a tool called loop cut, by which you can increase the number of vertices so that it would be more convenient and gives you more control over bending. And then we have increased the number of cuts to 40 so that we have more control for bending. And then we need to have, as discussed above, we need to have a pivot point to bend, such as for that we took a plane, an empty plane, with respect to which we bend the this long rod-like structure. And then we have set the axis to the empty plane that we have taken before, and then we have bent it with a degree of 180, and then we have dragged it so that the center of the plane and the center of the curvature would coincide, thereby forming a bent structure of a horizontal rod. So that's all about shape modification tools. Thank you.